Okay, here we go. So we're going to walk through the answer key to quiz number 1. So this was the problem you were given. You have a nitrile, and we're doing acid catalysis with acidic water, and we're turning that into an amide. Now, if you want, what would be really good is if you go back and review your notes from the alkyne chapter with triple bonds. You'll see that we did a reaction very similar to this, where we had a triple bond, we treated it with acidic water, and we ended up with the hydrolysis of the triple bond, making an enol, and the enol tautomerized to the keto form, which in that case was a ketone. If you go back and look at those notes, you'll see that the steps in the mechanism for this problem are going to be almost exactly the same as the mechanism that we did for the acid catalyzed hydrolysis of a triple bond to make a ketone, except now we're going to do it on a nitrile. So let's get started. First thing we want to do is we always want to check our pH, and when we look at the pH right here, we say, okay, over the arrow, we have acidic pH. That means let's keep everything at neutral charges or positive charges, but no negative charges anywhere throughout the mechanism, okay? So I'm going to put a plus sign here on the top right-hand side and keep track of that as my, my charge check to make sure that I don't violate that. So here we go. The first step is going to be, you're going to take the lone pair of electrons on the nitrogen, and that's going to be your nucleophile, and that's going to go after the proton as the electrophile, pick up the proton. And that was a step that I was very, very happy that probably the large majority of the students in the class did, in fact, choose that as the first step, where the lone pair go after the H+. Some students actually did this. Let me erase this. Some students actually said, for the first step, we're going to go from here to there, to pick up the proton. Now, that would be true if we were doing this on a triple bond where both ends of that triple bond were a carbon. But here we've got a nitrogen on one end and a carbon on the other end, and that nitrogen has a lone pair of electrons on it. And if you remember your atomic orbital and molecular orbital theories where you have bonding orbitals and then non-bonding orbitals and then anti-bonding orbitals, well, the lone pair of electrons on the nitrogen are the non-bonding, right? So they're in the middle here. This is your non-bonding electrons, which are higher energy than your bonding electrons. So you have a choice. You could use the bonding electrons in the triple bond to be your nucleophile, or you could use your non-bonding electrons to be the nucleophile in the nitrogen. The non-bonding electrons are higher energy. They're more like valence electrons. They're higher energy. They're more available. They're more ready and willing to do that work. Why would you want to choose bonding electrons when you could use the higher energy, more available non-bonding electrons to be able to get that to work, okay? So you want to take that lone pair, pick up the proton, and that's going to be step number 1. For step number 2, we have this ammonium ion here, and there's 2 resonance contributors for this if you think about it. So we have this one here, and we also have one where we can resonate these electrons here, and that's going to give us another resonance form of the ion, which can look like this. And now that you have this, you can see how you're going to make that carbon-oxygen bond, because if you go back and look at the starting material that you're working with, somehow in this mechanism, you have to figure out, how do I make a carbon-oxygen bond in order to get that carbonyl put in place? So here what we're going to do is we're going to take the best nucleophile, goes after the best electrophile, and we're going to go after the carbon now and make the carbon-oxygen bond, okay? And that's going to give us this, and then of course we've seen this step a lot of times where we're going to take a general base, your general base, well, let's not talk about what it is in this reaction. It could be a number, one of a number of things, but always remember, if you don't want to lose points, safest way to do it is to use the general base symbol to say best nucleophile goes after best electrophile, pull off the proton there. Because if you think about it, what is the pKa of this proton on that oxygen? Well, remember, alcohols have pKas of like 16, 17, but this is not an alcohol, that's an oxonium ion, and that pK is going to drop down to -2. So that's way more acidic than a typical alcohol. So any general base, any solid molecule will easily take off that proton and leave it with an alcohol, and there you have your alcohol. But then again, this is not an alcohol, right? Look at this. It's an alcohol attached to a carbon with a double bond. That's an enol. Now, we call that an enol when it was a carbon-carbon double bond. Here, it's a carbon-nitrogen double bond. So really, if we wanted to be technical, we would say this is called an iminol, I-M-I-N-O-L. Why do I say iminol instead of enol? Well, because an enol looks like this. And what we're looking at here is this. And so we've replaced this carbon with this nitrogen. And we're going to learn in a future chapter that when you have carbon-nitrogen double bonds, just like carbon-carbon double bonds, so if we have a carbon-carbon single bond, we call that an alkene. If we have a carbon-nitrogen single bond, that's called an amine. If we have a carbon-carbon double bond, that's called an alkene. If we have a carbon-nitrogen double bond, this is called an imine. So that's spelled I-M-I-N-E. And so just like we say, the alkene becomes the enol, the imine becomes the iminol. So it's a little bit of nomenclature there, but let's push forward with the mechanism. So get rid of this. So we're going to pick up a proton onto the iminol, because remember, just like you did when you saw enols, when you see them in the mechanism, before you can blink, they're gone. They're going to tautomerize back to their keto form because it's going to be thermodynamically more stable to have the carbon-oxygen double bond being present there. So we're going to do the same thing here. Well, we're going to do it stepwise though, right? So we're going to have the electrons on the nitrogen. We have a lone pair there. And we're going to have those go after the proton, pick it up. And so we have the nitrogen nucleophile after the electrophile, and that's going to get us to here. Now, a number of people, we're doing steps in this mechanism where you're putting, I saw 2, 3, 4, 5 arrows with electrons in one step. Remember, we don't do that. If we have a way of doing things stepwise, we will do it stepwise. The molecule will do it stepwise. So I'm not going to skip steps here and do the enol tautomerization one big step. I'm just going to go stepwise. I think it's actually easier to think about doing it stepwise because you don't have to focus on so many things at once. So now that we have this iminium ion, we'll do another resonance contributor. So don't forget, we have a lone pair of electrons on the oxygen. And we're going to use those electrons to make the double bond after we do this resonance contributor. So nucleophile after electrophile, that gets us to here. Now we have the carbon plus charge. So now we can see why the electrons in the oxygen are going to come down onto the carbon. That's going to be your carbonyl bond right there. And then once you have the double bond, again, we have an alcohol with an OH pK of about 16, 17. But now once you've made it a carbonyl, and that's an oxonic ion, pK drops down about -2, -3. So when that happens, any old base, so the general base symbol again is going to be used here, is going to come here, pick up the proton, leave the electrons behind on the oxygen for its lone pair, and that gets you to the final product. So that's the full mechanism and everything we were looking for. And the gradient of the mechanism was going to be, did you have all the right charges? No negative charges should have been shown anywhere. We're also looking for were all the electrons being shown which way they were moving. Remember, every single arrow you draw has to show motion of electrons. And so real quick here, just to show you what we're looking for is, and I'll do this in green, okay? Okay, so here we go. So we have nucleophile goes after electrophile. 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 Nucleophile, electrophile, nucleophile, electrophile, nucleophile, electrophile, nucleophile, electrophile. And that gets you to find a product. So every step is one that should be doable. It's really just an organization of steps we've seen previously in other reactions, other reaction mechanisms. Reorder them around a little bit, and you come up with this mechanism here. If you want to give this one a name, if you want to look it up, like say Wikipedia, the name of this would be called acid catalyzed hydrolysis of a nitrile to an amide. Okay, so if you have any questions about that, shoot me an email, and we can chat about it online, or we'll be in class and we can talk about this in class briefly at the start of class tomorrow night.